All right, hello class. In this video today, we're going to take a look at how do we calculate the pH after we've mixed together an acid and a base with each other. Now, we might immediately think, well, it's going to be 7, neutral, but there's a couple things here. Number one, sometimes at the end of the reaction, we have an excess of the acid that's involved. Sometimes we have an excess of the base. And it turns out that the pH is only 7 when they're equal for one of these three types of reactions. So we're going to be looking at what happens in a strong acid, strong base reaction, a weak acid, strong base reaction, and then a weak base, strong acid reaction. Each time, there's a few things I want you to be aware of. Your first step should be to write the net ionic equation. Your second step should be to show how the mole amounts you have react with each other. And then you need to do a calculation, potentially, from the excess that you have. Having said all of this, you really need to be able to identify if the acid or base is strong or weak. That has to be the thing. This is why I want you to know those 6 strong acids and 8 strong bases. If you know those, any other acid must be weak. Any other base must be weak. And we'll use that as we move forward. So we're going to start with strong acid, strong base calculations. And this is the information we want to be familiar with. At the end, if we have excess of the strong acid, we need to find H3O+, and then we're going to plug that into our pH equation to calculate pH. If we have excess of the strong base, that means we must have excess OH-, find POH, and then find pH. Strong acid, strong base is probably the most straightforward of calculations, so we're only going to look at really one of those very quickly. And then we will jump into the more complex ones, which is what happens when a weak acid and a strong base react. And what happens if there's leftover weak acid? What happens if there's equal amounts of them? What happens if there's excess of that strong base? This lesson is broken up into 2 parts. By the end of these 2 parts, you should be able to fill out this table, and the next video will start with this table filled out. I'm not going to fill out what these pieces are here just yet, but for today, we're going to focus on the strong acid, strong base calculations that take place when we mix them together, and what happens when we do just a couple weak acid, strong base reactions as well. So we're going to begin with strong acid, strong base reactions. In a strong acid, strong base reaction, we will always make water and a salt. But we don't always want to have to rewrite the reactions like this. We want to write what we call the net ionic equation. As a reminder to you, the net ionic equation tells us the ions in the reaction, they're actually involved. They're not spectators, they're the ones that actually change phase and change state of matter. To write net ionic equations, you need to look at each of the substances, and if it is an ionic compound or a strong acid or a strong base, it will break up into its ions. So for this reaction, it's going to look like this. Each of these 3 substances here will break up into their ions to make the complete ionic equation. Water will not. It's not an ionic compound. It's a molecular covalent compound. We're only breaking up things that are strong electrolytes. And then we can cancel out the things that we see on both sides. So Br- is on both sides, Rb+ is on both sides. Those are going to be our spectator ions, which means the net ionic equation for a strong acid, strong base reaction is going to be H+ plus OH- makes water. And folks, this is the net ionic equation for every single strong acid, strong base reaction. Writing the net ionic equation is important because we're going to use it in what we call a BSA table. A BSA table is similar to an ICE table in that you're measuring something at a beginning and at an ending point, but we use mole amounts for these because this is how the substances react. They react stoichiometrically. So rewrite the net ionic equation over here and label BSA for me. And what we're going to do is we're going to solve this question together. So in this question, I want to know what the pH is after I've added 35 milliliters of 0.2 molar HBr with 25 milliliters of 0.25 molar RbOH. So as we're in the react step at the moment, we've already written the equation. We need to find what the mole amounts of HBr and RbOH are. We're going to use volume times molarity in order to get moles. So when I do this math, I get that the mole amount of HBr is 0.007 with more zeros for sig figs, and then for RbOH it's 0.006250 to have correct sig figs. And I plug these numbers into my BSA table. I plug in the amount from HBr for H plus, because that's going to be what that actual molarity of or mole amount, of H plus is, and then I plug in this mole amount here for OH minus. And within a BSA table, it's very similar to that ice table structure. We're going to subtract, and we're going to subtract by the smallest amount, because what must happen with a strong, anytime a strong acid or a strong base is involved, is the reaction goes to completion. All right, it goes fully to the right-hand side. And so we're going to react and use up the smallest amount here. So with this, that means that at the end of the reaction, I don't have any OH minus left. But what I do have left is a very, very small amount of H plus. So if I want to know the pH at the end of the reaction, it's going to be dependent upon this amount. Now, we're not going to do that math right here. We've done these kinds of calculations, but you need to take this mole amount and you need to find the molarity of what H plus is. So that means we're going to divide it by 0.0600. And for those of you wondering why that is, please remember that we've combined two different volumes with each other. So the new volume at the end of this reaction is 60 milliliters, which is 0.0600 liters. Once you know the molarity of H plus, you can plug that into your pH equation in order to get what the pH is for the reaction. Now, if you have equal amounts of H plus and OH minus, that means it has to be a pH of 7. If you have an excess of OH minus at the end, that means that you will do the same thing, but you're finding the molarity of OH minus. So when you plug that in and take the negative log of it, you find POH before you can then subtract from 14 to get pH. This is the basis of how we're going to calculate pH at the end of a reaction for strong acid, strong base reactions. Weak acid, strong base is a little bit trickier, and we're going to start that now. A reminder to you, we're going to follow the same structure for these kinds of questions. We're trying to find the pH after the reaction. We have to first write an equation. For weak acid, strong base reactions, the reaction always creates the conjugate base of the weak acid involved. Now, here's a generic reaction for you. It's using NaOH as a strong base, where this could be RbOH or KOH or any of your other strong bases. But HA is our symbol for a generic weak acid that is involved. And you can see in the reaction that we create A minus. And we'll talk about that in just a moment. So for this reaction here, which is using HClO, hypochlorous acid, I believe is its name, reacting with sodium hydroxide, we do not need to have this entire thing. We just want the net ionic equation. What are the substances that are actually reacting, the ions that are actually reacting? Well, we cannot break up HClO because it's not a strong electrolyte, it's a weak electrolyte. So we're going to leave that exactly as it is. NaOH we can break up because it's a strong electrolyte, it's a strong base, so that will become OH minus. And then over here, NaClO is an ionic compound, and so we can break that up into its ions. When we do so, we're going to ignore the Na because it's a spectator, so Na plus shows up on both sides. It's a product and a reactant, so we're going to ignore that. And then we get water. So this is what the net ionic equations should look like, roughly, for a weak acid, strong base reaction. That's step one. The next thing we need to do is we need to create a BSA table in order to show how these things react to figure out what we have left over at the end. So the first step is to find the mole amounts of each of the reactants that you have in this question. We have 25 mils of 0.25 molar HClO and 25 mils, so same volume, but a much bigger molarity, 0.5 molar of NaOH. And so to calculate this, we do use the molarity equation, and we get that this is our mole amount of HClO, and this is our mole amount of NaOH. So then the next step is I'm going to plug them into my BSA table, because we want to figure out this reaction is going to go to completion. Strong acid, strong base forces that, or the presence of a strong acid or a strong base forces that, and we have, within this question, a strong base. So I'm going to plug in those amounts, and then I'm going to subtract the smallest amount from both of them. This means I'm going to have none of the HClO left over at the end, but I will have about half of the OH minus left over at the end of the reaction. Now, I do want to note here that technically we do gain some of the conjugate base of this weak acid. So there is some amount of this that's present at equilibrium. However, it's going to be so small in comparison to the OH minus that the OH minus is what dictates the pH at the end of the reaction. So we're going to kind of ignore this for the moment, and we're going to need to calculate what our new OH minus concentration is. Well, we mix together 25 mils and 25 mils. So my new final volume then is 0.0500 liters. And so from this, we're going to get what the molarity of OH minus is, and then to get pH, we're going to plug this number into the take the negative logarithm of it to get POH, and then subtract from 14 to get pH, and I will let you do that independently. Okay, our last calculation in this video is again going to be for weak acid, strong base, and it's going to be when we combine equal amounts of the weak acid and strong base with each other. So I've rewritten the overall reaction, I've rewritten the net ionic equation here, and you can see underneath the weak acid I've got the volume and the molarity, and I've got the volume and the molarity of the strong base. And because all the numbers are the same, we must have the same mole amounts of HClO and OH minus. So the equation step's already done. We're in the reaction phase. We're going to plug in these mole amounts and figure out what is left over at the end of this reaction. So when I plug these numbers into my BSA table, I'm in this reaction step, I get that I have none of the weak acid left at the end of the reaction, and I have none of the OH minus left at the end of the reaction. But I did create 0.006250 moles of ClO minus, which is the conjugate base of HClO. Now, what kind of base is this if it's not one of your strongs? It's a weak base. So at the end of this reaction, I have the presence of a weak base in water, and we know that weak bases will react with water ever so slightly to create an equilibrium that looks like this. So the takeaway that we want to have here is that once we figured out this reaction part in step 2, when we have equal amounts of a weak and a strong, we have to look at what that weak substance is that is left over at the end. In this case, we have a weak base. Bases accept protons, and so ClO minus accepts a proton from the only other thing that's around, water, and in doing so, it creates the conjugate acid and OH minus. This means an equilibrium forms, which means in order for us to find pH, we need to make an ice table. So folks, when you're creating this ice table, what you need to do is you need to find the molarity of the ClO minus ion that's left at the end. So you take the mole amount and you plug it into M equals N over V, and I got this volume because at the end of the reaction, I combined 25 mils and 25 mils, I have 50 mils. Which is this, and this is the molarity. Now folks, I'm not going to work through this ice table completely, because at this point in time, if you're up to date on your homework packet, we have done these calculations before. But what we will do, because it's a weak base, is we'll make the assumption that the amount B in comparison to 0.1250 is going to be negligible, so we can ignore it, but we'll add B on these sides. And then we have to plug all of this into our Kb expression and solve for B. Once we know B, we know OH minus. Once we know OH minus, we can find POH, and then we can find pH. Now, Kb might be directly given to you, or in a question like this, oftentimes what you're told is you're told the Ka value of this weak acid, and this is where we need to remember that Ka times Kb for a weak conjugate acid base pair equals 1 times 10 to the negative 14. So you can find the Kb from that. As you can hopefully see by the end of this video, there is a reason why it's split up into 2 parts, and there's a lot of different math that we're doing here. So We're going to fill out that kind of front little bit to help keep track of what do we do when we know what is left over at the end of the reaction that you saw on the first slide of this video. But the thing that I really need you to know is that these are the steps that we need to do. Number 1, write the net ionic equation. Number 2, make a BSA table that shows what reacts and what's left over. And then use what's left over at the end to figure out how to proceed from here. Thank you very much for listening. We'll go through this in class. Thanks.